So for this problem, we're looking at a cooling tower example. So to start off, we're given that the tower is 10 meters tall. And it's got a cross-sectional area of 100 meters squared. We're given that the water coming in from the top is coming in at 70 degrees Celsius, and the mass flow rate is 50 kilograms per second. And then we have air coming in from the bottom at 5 meters per second. That's its superficial velocity. And then it's exiting the top at 90% relative humidity and 40 degrees Celsius. The tower itself has diagonal slats throughout to increase the surface area contact between the water and the air. So that area of contact we're given is 5 meters squared per meter cubed. So, and then also from what we're given, we can figure out the mass flow rate per area of the water. So that's just the 50 kilograms per second divided by the 100 meters squared. So that's 0.5 kilogram meters squared times seconds. The heat transfer coefficient that we're given from water to air is 10 watts per meter squared degrees Kelvin. And we can assume in this problem that the Lewis number is equal to 1. So what the first problem is asking us is to derive the differential equations to determine the temperature for water, the temperature for air, and the mole fractions of water and air at any point along the z-axis of this column. So to get right into it, we'll go ahead and look at how to derive the differential equation for the temperature of the water throughout the column. So first thing we're going to do is we're going to start by drawing a controlled volume for reference. So we'll go ahead and draw our box here. So we have our water coming in. So this is our temperature of our water in and the temperature of our water coming out. We can also express this as the enthalpy of the water, both going in and going out. And then we also have the temperature of the air coming in. That's our air. And we can also express our mole fraction of water that's now going to be in our vapor phase as the air moves through. So what we'll do is, so this is our DZ, this is our change in position throughout the column. Right off the bat, we'll go ahead and define this direction. Since we're looking for the equation for our temperature change in water, since water is moving in this direction, we'll go ahead and establish that this is our positive z direction going down. So in order to find this, we've got to do an energy balance. So first things first, we want to look at what's going in for the water stream. So we want to look at our mass flow rate of our water coming in, which is going to be what our water is coming out. So we can go ahead and first just look at our GW, which we defined up here already. And we'll multiply that by our cross-sectional area, because ultimately what this will give us is this will give us our units of kilograms per second, but we'll just utilize this as a convenience factor rather than just putting singularly our mass flow rate from right at the beginning. Next thing we want to multiply this by is the heat capacity of water. This will help account for the change in temperature of the water. And then we'll multiply that by our DT, or our change in temperature of our water. So this will give us our energy on our inlet side of the column, so the water going in. Now we've got to compare it to what is going to be coming out on the bottom end of the column. So first things we got to do is again, we're going to have our total area of contact times our cross-sectional area. So this is essentially just going to give us our contact per volume. Sorry. Also with our change in position. This will give us our contact per volume throughout the tower. And then we want to look at the concentration of the water throughout the column. So when we're looking at each individual slats here, where our water is making contact with the air, we can think of that as a singular individual interface between the air and the water. So if we drew our interface like so, where we have water on one side, we have air on the other side, there's going to be concentration of water comparatively to air at both the interface here. So we can say that's our concentration of water at the interface versus the concentration of the water in the vapor phase, compared to our bulk air phase. So we can express that then as concentration of water in our bulk phase. So we also need to show how these concentrations relate to each other. So we need to know that the rate at which the water vapor transfers to the bulk air phase, that's directly related to the differences in concentrations between the water in the interface and in the bulk phase. So we can just simply write that as, again, the difference between the two. So the concentration at the interface minus the concentration of water in the bulk phase. And we'll write it this way because the concentration of water at the interface is going to be larger than the concentration of the water in the bulk phase. So the next thing we'll add is just our Kc value, as well as our heat of vaporization of water, which we're going to make that value negative. And we're going to do that because this quantity here, like I was saying before, since the concentration of our water at the interface is going to be greater than our concentration of water in the bulk phase, this value here is going to be positive. And since that's going to be positive, if this quantity remained positive, that would show that this change in temperature would be increasing as we go down the column, which is not what we want. What we're trying to show is that as the water moves down the cooling tower, it's going to be cooled, so the temperature is going to decrease. So we'll put a negative sign there so that it represents a decrease in temperature as we go down the column in the positive z direction. Last thing we need to do is we need to show an expression for the rate of heat transfer from air to water. So we can simply just show that kind of like as an H delta T expression. So really all we need is to add to here, we'll just add our heat transfer coefficient that we're given, our convective heat transfer coefficient, times our change in temperature from our air to our water. So we can just simply do temperature of our air minus the temperature of our water. And this is going to be our first differential equation. So this is just showing then the change in the temperature of the water throughout the column as the water moves downwards. And so the next one that we have to work at is our change in air temperature throughout the column. So we're going to follow a similar path. So for that, we'll go ahead and again, we'll draw our constant situation here. Oops. Water's going down. So again, we can show that the enthalpy of the water going in and coming out, as well as the enthalpy of the air going in and the enthalpy of the air going out. So what we didn't show before is that since this is a steady state example, we know that up here and down here, our difference in enthalpy of our air and our water is going to be the same as on the bottom. So essentially what that means is that our change is going to be equal to 0. So essentially what we can say from this then is that our enthalpy of air minus our enthalpy of water is equal to 0. So our change in enthalpy of air is then equal to our change in enthalpy of water. So again, we'll follow the very similar path that we did for this one. So essentially we just have to look at what is now the flow rate of the vapor phase, which is essentially just the air. So what we'll express is that instead of G of just air, since in the vapor phase we have both the air and the water vapor, so we'll express that as a singular big G, and we'll classify this G as the sum of the gaseous flow rates. So that's just equal to the flow rate of A plus the flow rate of water in the vapor phase. And again, we'll just express, again, the cross-sectional area times the heat capacity of the air times the change in temperature of the air. And that'll give our energy of the air on the inlet coming in. And then on the other side, we can actually express it in the same exact fashion as we did before. So we can just use this side of the equation. So I'll go ahead and write that. And really what this is showing, what this differential equation is showing, is this half here, this is expressing essentially like our change in enthalpy of air throughout the column, whereas this, and then this half is essentially showing our change in enthalpy of water. So this is our second differential equation that's showing the change in air temperature as the air moves up through the column. So now for the last part of the third question, we want to look at the change in mole fraction of water in air at any position throughout the column. So in order to do that, we're going to go ahead and we're going to work on doing a mass balance rather than an energy balance. So first thing that we want to do is we want to show the mass flow rate of air going up through the column. So we can first express that as, again, the cross-sectional area times our gaseous flow rate of air. So that'll give us some units of kilograms per second. So essentially then what this is equal to is our density of our gas times the volumetric flow rate, which this will also give us units of kilograms per second, which can also be expressed as, again, why we're using this as a convenient factor. This is also equal to the pressure times the average molecular weight of our vapor phase over RT times our volume times our cross-sectional area. And you'll see that this also gives us units of kilograms per second if you do all the units out. And you can also see that now our units for, or our variables for our cross-sectional area can cancel out. So we're left with kind of this expression here. So we need to also identify what our average molecular weight is. So what we know from previous work is that our average molecular weight, we can express that as our flow rate per area of our water in the vapor phase plus flow rate per area of our air divided by flow rate of water over the molecular weight of water plus flow rate of air over molecular weight of air. And from this, we know that flow rate of water in the vapor divided by the molecular weight of water, we can then express that as the mole fraction of water times the overall gaseous flow rate per area over the average molecular weight. Then we can rewrite this even further to solve for our flow rate for water. So then that's just equal to the mole fraction times our overall flow times the molecular weight of water all over our average molecular weight. So now getting right into our differential equation for a mole fraction of water in air, we want to express that in terms of a mole fraction. So we'll go ahead and look straight at what we were kind of doing before. So we want to look at, again, the cross-sectional area times our overall gaseous flow rate per area. And what we'll end up doing is we'll multiply that by our change in mole fraction. So right now this is in terms of mass, this is in terms of kilograms. We want to make that in terms of moles. So we'll go ahead and divide that by our average molecular weight, because then on this side that'll show our molar flow rate, so our moles per second. This is the total molar flow rate going up the tower, and we'll set that equal to, again, similar to what we did before. So we'll do our area of contact times our cross-sectional area times our change in position, and we need an expression that's essentially the molar flux. So our flow rate, our molar flow rate per area. So again, we can just use our Kc value, and if we just multiply that by our concentration of water at both our interface minus our concentration of water in our bulk phase, this expression is essentially just our molar flux. And if we want to relate this part of our expression back to pressure, we can simply just show that Cw at the interface is just equal to our pressure of water in the vapor phase divided by RT. And then the concentration of water in our bulk phase is just equal to the mole fraction of water times our gaseous pressure divided by RT. So again, now this is essentially our third differential equation here. Now the last thing that we need to do before we can call it quits is we need to define our Kc value. We keep using Kc, but we need to define an expression for Kc. So first things first is we were told at the beginning that our Nusselt number is equal to 0.6 times the Reynolds number to the 1/2 times Prandtl number to the 1/3. And we're given that our Lewis number is equal to 1. So right off the bat, we'll first start off by looking at the Lewis number. So our Lewis number is actually just equal to our Schmidt number divided by the Prandtl number, which if we break that down into each dimensionless component's variables, our Schmidt number is equal to our viscosity divided by rho, which is our essentially our kinematic viscosity, divided by our diffusivity constant. And then our Prandtl number is equal to, again, our kinematic viscosity over our K value, or our thermal conductivity, sorry. So from this, cancel those out. And this essentially leaves us with our thermal conductivity over rho Cp times our diffusion coefficient. So then we can rearrange this. Actually, we'll hold off on that. So what we want to show first is our heat transfer analogy. So we can also show that not only is our Nusselt number equal to 0.6 Reynolds number to 1/2 Prandtl number to 1/3, but we can also show that the Sherwood number is equal to 0.6, then in this case, Reynolds number to 1/2, our Schmidt number to 1/3. So what we can go ahead and do is divide our our Sherwood number by our Nusselt number, and our Sherwood number can be defined as Kc, a familiar variable we're looking for here, times some characteristic length all over our diffusion coefficient AB. And then our Nusselt number can also be defined as our heat transfer coefficient times, again, a characteristic length all over the thermal conductivity. Now you can see that characteristic lengths will cancel out. And this is essentially showing that our Schmidt number over our Prandtl number to the 1/3, this is also what it's equal to. So that essentially just means that this, whoops, that was bad, quantity here is equal to Lewis number to the 1/3. So then what we can show from here is that Kc over H, our heat transfer coefficient, convective heat transfer coefficient, times our thermal conductivity over our diffusion coefficient is equal to our Lewis number to the 1/3 power. And since we have this expression here, which we'll come back to now, we can show that we have a familiar set of variables here and here. So what we can show is that our thermal conductivity over our diffusion coefficient is equal to rho CP times our Lewis number. So what we can do, we can plug that in. So now Kc over H is the same times this quantity here. We can say rho Cp times the Lewis number equals Lewis number to the 1/3. And since we were told at the beginning that the Lewis number in this problem is essentially equal to 1, we can rewrite this as just Kc over H times rho Cp is equal to 1. So then our value for Kc, or expression for Kc, can be rewritten as Kc is equal to our convective heat transfer coefficient over our density times our heat capacity. So all in all, we have three differential equations that came out of this. Our first one, and those are three derived differential equations.